Welcome to the class activities for Lesson 19, College Algebra, Math 107. Which of the following graphs represent functions that have inverse functions? So this is also known as being one-to-one, and we check it by using the horizontal line test. So we draw a horizontal line. If it intersects in more than one place, then its inverse is not a function, and we say it is not one-to-one. So this one's a no. This one, I can draw horizontal lines anywhere, and it always only intersects once, so this one is a yes. It has an inverse function, and it is one-to-one. Find the inverse of f of x equals x cubed plus 1. So our process was the switch and solve strategy, so we write y equals x cubed plus 1. Make the x's y's and the y's x's, and then solve for the y. So I'm going to start by subtracting 1. So I have y cubed equals x minus 1. And then to undo cubing, I would cube root. So I get y equals the cube root of x minus 1. And finally, replace the y with the notation f inverse of x. Cube root of x minus 1. All right, let's look at the function g of x, which is x squared minus 1. How has the graph of f of x equals x squared been transformed to create the graph of g of x equals x squared minus 1? Well, that is a vertical shift down 1 unit. So since I know what x squared looks like, I can sketch g of x. There's my 1 vertical unit. And then g of x is going to look like this. Since g of x equals x squared minus 1. Okay. Is g of x one-to-one? Does it pass the horizontal line test? No. No, it does not. There are lots of places where I can draw a horizontal line and it will intersect my graph in more than one spot. But I could fix it, right? I could erase part of g of x and force it to pass the horizontal line test if I erase either the left side or the right side. So if I erase half of this graph so that it looks just like that, put my axis back in there, and I define g of x so that it's equal to x squared plus 1, but only to the right of the y-axis, my new restricted domain is x is bigger than or equal to 0. So I've just deleted half of the graph. That's what a restricted domain means. I'm restricting g of x to be x squared minus 1, but only for x's that are positive or 0. And now that I've restricted the domain, now I can find the inverse using our switch and solve strategy. So I say y equals x squared minus 1, switch, x equals y squared minus 1, and solve for y. So add 1 to both sides, so I have y squared equals x plus 1. And then here's where it gets tricky. Usually when you take the square root of both sides, you end up with a plus or minus on the x plus 1, on the square root of x plus 1. But because x is restricted to be positive, then my square root is going to be restricted to be positive, right? So y is going to be the square root, the positive square root of x plus 1. All right, so if we're given a formula, you can find a formula for the inverse. But if you're given a graph of a function, you can sketch a graph of its inverse, even if you have no formulas. Because the definition of what an inverse does is it reverses the role of input and output. So you can look at some points, list a few nice points on F. So let's see, I've got 0, 1, that one, 1, 2, 2, 4, 3, 8, and then maybe I'll do a negative x, like negative 1. That looks like maybe a half. and -2 1/4. So there's a few points on F. The corresponding points on F inverse, right, just reverse the components of the points on F. So I have 1, 0, 2, 1, 4, 2, 8, 3, 1/2, -1, and 1/4, -2. Plot your new points. 1, 0, 2, 1, 4, 2, 8, 3, and 1/2, -1, 1/4, -2, and then connect your points with a nice smooth curve. And you see that my pink curve that I just drew is the reflection of the original curve over this line that's dashed here, which is the line y = x. So it's a mirror reflection over the line y = x. All right, let's look at the domain and range of f and f inverse. So f, the original function graphed as a black line here, its domain is -∞ to infinity, and its range is 0 to infinity. And then my pink graph, its domain is 0 to infinity, and its range is -∞ to infinity. So the domain and range of f and f inverse swap, right? The domain of f becomes the range of f inverse. The range of f is the domain of f inverse. So just one more practice. I'm going to sketch f inverse here. This is a graph of f. It's a simple piecewise linear function. So I'm just going to reverse the components of these 3 important points and sketch the inverse. So instead of -3, -2, I'm going to plot -2, -3. And instead of -1, 0, I'm going to plot 0, -1. And instead of 4, 2, I'm going to plot 2, 4. Connect those points. And you can see that they do form a mirror image over the line y = x that I just sketched in green. All right, I just want to look at the domain and range. For f, which is my blue graph here, its domain, smallest x to biggest x, would be -3 to 4. And its range, smallest y to biggest y, would be -2 to 2. And then f inverse, what I graphed in pink, its domain, smallest x to biggest x, would be -2 to 2. And its range, smallest y to biggest y, -3 to 4. And again, you can see the swapping of the domain and range for f and f inverse. All right, we've got some statements here. We're going to determine if they're true or false. All one-to-one functions have inverse functions. True. It's one-to-one. Its inverse is a function. The inverse of f of x = x squared is f inverse of x equals the square root of x. No, this is false. It's close. It's very, very close, but you have to restrict the domain, right? This is only true if you define f of x to be x squared if x is bigger than or equal to 0. So you have to restrict the domain in order to be able to do the switch and solve strategy. And then f composed with f inverse of 2.5 is 2.5. That is true, right? Because inverse functions undo each other. So if you plug a 2.5 into f inverse machine, right? F inverse and f are machines that undo what the other one did, right? So if I put a 2.5 into f inverse, something comes out, I don't know. But F undoes whatever F inverse did. So whatever came out of F inverse, you put it into F, 2.5 should come back out. All right, we're going to look at practice finding inverse functions, formulas, and graphs. So we're supposed to first look at the graph, determine if F is 1 to 1. If it is 1 to 1, sketch a graph of its inverse by plotting, switching some x and y coordinates. And then, if possible, find an equation for F inverse. We're not going to do it for 5, 6, 7, and 8, but 1 through 4, we can find a formula. So f of x is negative 2x plus 1. So first, I look at the graph. I say, oh, that passes the horizontal line test, which means it has an inverse. So I will proceed to try to find it. So if I want to sketch the graph here, I'm going to pick a few nice points on this function. I really only need 2 because you only need 2 points to determine a line. And I'm going to swap the x and the y coordinate. So this point right here is at negative 1, 3. Swap the coordinates and you get 3, negative 1. And then my next pink point there is at 0, 1. Swap the coordinates and you get 1, 0. And then finally, I have 2, negative 3. Swap the coordinates and you get negative 3, 2. Connect those 3 points. I didn't do that very well. There we go. And they do look like they reflect over the line y equals x, or mirrors over the line y equals x. All right, so the last thing I'm going to do is try to find a formula for the inverse. Using the switch and solve strategy. So I've got y equals negative 2x plus 1. Make the y's x's and the x's y's. Solve for the y. So I have negative 2y equals x minus 1. Divide both sides by negative 2. There's my inverse function. All right, number 2. Start by saying, does this pass the horizontal line test? It is hard to tell because it kind of flattens out near the x-axis. But if we were to graph this on a calculator or a computer and zoom in, you would see that it doesn't ever get fully flat. So it does pass the horizontal line test. So I pick a few key points on here. So that's a key point. And then there aren't any other really good integer ones, so I'll just have to do some estimating. Maybe that one, and that one, maybe that one, and that one. And swap their coordinates. So this one in the middle, that's at 2, 0, so 0, 2 is definitely going to be on my inverse graph. And then this one here, that looks like, I don't know, 3 1/4, comma 1. So 1, comma 3 1/4 should be on the inverse. And then that one looks like 4, 3, or pretty close to it. So I'm going to plot 3, 4. All right, and then this one looks like it's at a half, negative 1. So I'm going to go negative 1, a half, and plot a point. And then that one looks like 0, negative 3, or pretty close to it. So I'm going to go negative 3, 0. And then I'm going to try to connect these with a nice smooth curve. Is definitely not perfect because I had to estimate some of my points. But you do see symmetry that we would expect over the line y equals x. You do see that mirror image over the line y equals x. All right, I want to solve this. I want to find f inverse using the switch and solve strategy. So I've got y equals 1/3 times x minus 2 cubed. Make the y an x and the x a y. And I want to get the y by itself. I'm going to start by multiplying both sides by 3. Then I'm going to cube root both sides. So I have the cube root of 3x equals y minus 2, and then add 2 to both sides. Y equals the cube root of 3x plus 2. And let's just quickly verify using some graphing software that that is the inverse, that it looks like what I got when I plotted points. Okay, so my original function is 1/3 x minus 2 cubed. All right, that looks like the graph we were given. All right, and then the inverse is the cube root of 3x plus 2. All right, I don't know the command for cube root, so I'm just going to use the 1/3 power since they mean the same thing. Raised to the 1/3. So instead of taking the cube root of 3x, I'm raising 3x to the 1/3, and then I still have to add 2. Oops, 3x to the 1/3 plus 2. And that is what I graphed. And this looks a little weird because of the scale. So let's see if I can just make it look a little more square. There we go. That looks better. Now you can see the symmetry over the line y equals x. All right, number 3, f of x equals -1/x. I look at the graph and I say, yep, that looks like it passes the horizontal line test. It has an inverse function, so I'm going to try to find it. Start by sketching it by choosing some nice points and swapping their coordinates. So that's a nice point, a nice integer point. I don't have any more integer ones, but that's not bad. And that's not bad. That should do it. And then I'll choose these ones down here. All right, so that point is at 1/2, 2. Swap the coordinates to be 2, 1/2, and it lands right there. This point is at -1, 1. Swap the coordinates, 1, -1, and it lands right there. -2, 1/2. Swap the coordinates, 1/2, -2, lands right there. Huh, landed on itself. All right, so this was this point, that one right there, is also on the graph. So it's at 2, -1/2. Swap the coordinates. So you get -1/2, 2, and I get that point. And I'm going to get that point, and I'm going to get that point. So if I connect them with a nice smooth curve, it is the original function. So let's verify that f of x equals -1/x is its own inverse by using the swap and solve strategy. So I have y equals -1/x. Swap the x's and the y's. And now I want to try to get that y by itself. So I'm going to multiply both sides by y, divide both sides by x, and that is my original formula. F inverse of x is -1/x, which is also f of x. So there's a function whose inverse is itself. All right, number 4, f of x equals 2x to the 3/8. Give it a quick glance, say, yep, that passes the horizontal line test. Pick a few nice integer points. Looks like I've got 0, 0, 1, 2, 3, 3. That should be enough. Swap the coordinates. So 0, 0 remains 0, 0. But then 1, 2 becomes 2, 1. And 3, 3 stays 3, 3. And connect those. And you do have a line that is a curve that is the mirror over the line y equals x. Let's find its formula using switch and solve. So make the y an x, make the x a y, get the y by itself. So I'm going to divide both sides by 2. So y to the 3/8 equals x over 2. And then to get the y by itself, I'm going to raise both sides to the 8/3. Right? Because when you raise a power to a power, you multiply the exponents, and 3/8 times 8/3 is 1. So that becomes y to the first, or just y, equals x over 2 to the 8/3. And that's my inverse function. All right, so for these last 4, all we have to do is check that it's a one-to-one function, and if so, sketch its inverse. We're not going to try to find a formula because these are much more complicated formulas. So for number 5, fails the horizontal line test. So I don't have to do anything else. Just write not one-to-one. Number 6, this does pass the horizontal line test. So I just have to sketch its inverse. Pick a few nice integer points here, swap their coordinates, and sketch the result. So this point up here looks like -2, 4. So I'm going to plot 4, -2. Do it in a different color. Okay, next pink point, -1, 1. So I'm going to swap it and plot 1, -1. And then 0, 0 stays 0, 0. 1, -1, swap it, -1, 1. And then 2, -4 becomes -4, 2. And I connect these with a nice smooth curve. Looks like that. Here we got a cubic polynomial. Looks like it passes the horizontal line test, so I just have to sketch its inverse by flipping some coordinates. So pick some nice integer points on here. That one's pretty close to an integer. That's a good one. Do the y-intercept. That's a good one. That seems good enough. All right. If once I plot those 4 points reversed, if I still can't see what the function will look like, I'll do some more points. So I have -2, 1. That becomes 1, -2. -1, 0 becomes 0, -1. 0, -1/2 becomes 1/2, 0. Oops. That was 0, -1/2, so that becomes -1/2, 0. And then 3, -3 becomes -3, 3. And see what this looks like. Something like that. And then this is probably going to go like that so that we can get the mirror effect. All right, last one, f of x equals 2 to the x. Pick a few nice integer points. It does pass the horizontal line test, so I just have to plot a few points here and reverse their coordinates. So this one down here, it looks like -2, 1/4. So I'm going to plot 1/4, -2. And then -1/2 becomes 1/2, -1. 0, 1 becomes 1, 0. 1, 2 becomes 2, 1. And 2, 4 becomes 4, 2. Connect those with a nice smooth curve. And we have the inverse of 2 to the x.